Anuragji on behalf of Group 2 standing before you for the demo lesson from the allotted topic for us, that is alkenes and alkynes. And from this we have selected a small and simple topic. So before discussing what is our topic, let us see here. So here you can see the photos of two brothers. So by seeing this picture, what comes to your mind first? Can somebody say?
Mirror.
They are twins. They are identical twins. So identical twins, they have they look similar, but they are entirely different personalities, and they have different behavior also. So just like this, in the world of chemistry, we have certain molecules which have the same molecular formula, but they differ in their properties. And such compounds are called isomers, and the phenomenon is called isomerism. So there we come to our topic for today, that is isomerism in alkenes. So we are reviewing our study in isomerism in alkenes. Now, as we have already learned in the previous chapter about the classification of isomerism, so we have isomerism is broadly classified into two types, that is structural isomerism and stereoisomerism. Again, the structural isomers, they have the same molecular formula, but they differ in the structures. And in structural isomerism, again, there are four branches. There is chain isomerism, position isomerism, function isomerism, and metamerism. And we have already learned about the second type of isomerism, that is stereoisomerism, which arises due to the difference in spatial arrangement of atoms. And that can be again broadly classified into two types, there is geometrical isomerism and optical isomerism. So let us learn about the structural isomerism in alkenes first. So for this, I am taking one example. So with the help of this example, let us learn about the structural isomerism. So here I am taking a molecular formula of an alkene. So you know that the molecular formula of alkene, the general formula of alkene is, can somebody please say?
CnH2n.
CnH2n. This is general formula. And if I am taking 4 carbon atom, the number of hydrogen atoms should be 8. C4H8. So now with this molecular formula, what all different ways of arrangement, that is in the form of in different structures, what all different structures we can derive from this molecular formula. Let us see. So there are 4 carbon atoms. So the first arrangement will be like, we can arrange the 4 carbon atom on a straight chain like this, and we can number them as carbon atom number 1, 2, 3, and 4. So since this is an alkene, obviously there will be a carbon-carbon double bond. So first let us place the carbon-carbon double bond in between 1 and 2 carbon atom. Now let us complete the valency of each and every carbon with the hydrogen. So here CH2, CH, CH2, CH2. So and this compound is but1ene. Now, is there any other possibility that any other structure is possible for this compound?
Yes.
Yes, we can have another structure also. So what will be that?
Position.
If it is a
Now
chain,
we can shift the position of the
double bond.
So now we will take the same chain, 4 carbon straight chain will take, and this time we are just shifting the position of the double bond from first position to the second position. Now we are filling the balance, the remaining balance of each carbon with hydrogen atoms. Okay. Now we got the second compound. Is it different from the first compound? Yes. What's the difference? The difference in position of the double bond. And this compound is but 2ene. Here the double bond is on second position. Now, again, so can we have any other structure possible with the same molecular formula? So we have already written two structures and we got two different compounds. Can we have? So this time we will try with a 3-carbon chain. There are 4 carbon total. So this time we will try with the 3-carbon main chain and the 4th carbon we will put as a branch. Okay. So now we have to put the double bond. So if I am putting double bond here and completing the valencies of carbon atom, we get this compound. Now, can anybody name this compound? Yes, ma'am.
2-methyl propene.
Very good. Thank you. This is 2-methyl. 2-methyl propene. Now, so here we have 3 different compounds. Now, can we shift this double bond here and get a new compound? Is it possible? Suppose if we shift the double bond over here, this hydrogen will go here and we are getting this compound. But are we getting a different compound or is it the same? It's the same because we are taking the parent chain. This will become our longest continuous chain of carbon atom, the parent chain, and this will become the branch. So we are getting the same compound. So and even if we keep here also the same thing happens. So with this arrangement we can have only one possibility, that is 2-methyl propene. Now here when we take these 3 compounds, now any other possibility with the same molecular formula? Any other structural isomer? Is it possible?
We have one more possibility.
Yes, sir.
A cyclic compound is found.
Yes.
Cyclic compound is also possible. But as far as class 11 concept, the cyclic compound we are not taking, so we are limiting our studies to these isomers. Now, when we compare the compounds 1 and 2, they differ only in the position of the double bond. Okay, so such isomers are called as position isomers. So they are structural isomers. They differ in the structure and especially in the position of the double bond. So we can have it. So when alkenes they differ in the position of double bond, then it is called having the same molecular formula, but they differ in the position of the double bond. They are called as position isomers. And again, so here if we take 1 and 2 are coming under position isomers. Now let us consider 1 and 3. 1 and 3. So are they position isomers? No. So means they have different means they differ in the position of the. They both differ in the position of the double bond in the carbon chain, the same carbon chain. But when we consider the third compound, the main carbon, the parent chain is different. So we can consider these two as the same means position isomers. But when we take the carbon skeleton, it contains 3 carbon parent chain and 1 branch. Whereas here we get a 4 carbon straight chain. So they both differ in the carbon skeleton. So they both the compound 1 and 3 comes under chain isomers. They differ in the carbon skeleton. And like that we can have one more pair. So can you please identify one more chain isomer from this? Between 2 and 3 also we can have chain isomers. Okay. So here, these are the different structural isomers possible from C4H8 molecular formula. 2 position isomers are there, and between 1 and 2 and 1 and 3 we can have chain isomers. Now, will alkenes exhibit geometrical isomers? Let us see with an activity. So for that activity, so before doing that activity, let us have a look at this compound. Here I have tried to make one ball and stick model of ethane molecule. Here these two round shaped dowel, they represents carbon atom, and the pins attached to it represent hydrogen atom. So I have attached 3 hydrogen atoms each with carbon, and you can also see a carbon-carbon single bond. Now, so when we are holding one carbon, and if we try to rotate the second carbon, are we able to rotate it freely? Yes. So free rotation around the carbon-carbon single bond is possible. Now let us take an alkene like this. So this is there is a carbon-carbon double bond. So this time we are trying the same with this alkene. Now I am holding one of the double bonded carbon atom, and I am trying to rotate the second double bonded carbon atom. Is it possible?
No.
No. So I cannot rotate it freely like in the first case. So that means the rotation around the carbon-carbon double bond is restricted. So since it is restricted, we can have different possibilities in arrangement of atoms attached to this double bonded carbon atom. So let us learn about this phenomena by doing an activity. So for that activity, I request our group leader Vivek sir as to play the part of carbon atom, and I request Anil sir to be second carbon, and please make
This is double bond.
double bond included. So now both the carbon atoms are having two valencies
Right to
to
rotate.
be satisfied. So I request
Other four members.
Anudeep madam and Sissy madam, and I need two male teachers, Dharmaraj sir and Deepak sir. Sorry, Rajesh.
हम दोनों
Now,
that's correct. That's correct.
No.
That's correct. Sir, Rajiv sir, you come in the transformer.
So
You come in the
so
transformer.
this is the carbon-carbon double bond. Now each of this carbon atom has two
So
valences.
this is his off.
Now one
On this side,
arrangement. Please hold the shoulder. Now this is one possible arrangement. So in this arrangement, we can see that the female teachers, they are on the same side of the double bond, and the male teachers are on the other side of the double bond. And this is one particular arrangement. Now, as I have told you that only restricted rotation is possible. What is the other arrangement? What way I can get a different compound? By interchanging the atoms or group attached to one of the double bonded carbon atom. So I'm just requesting Rajiv sir and Susi ma'am to change their position. Now, are we getting a different compound here? Yes, we have a different compound here. So in this arrangement, the female teacher and male teachers, they are coming on the same. Two female teachers are coming on the opposite side of the double bond, and two male teachers coming on the opposite side of the carbon-carbon double bond. So thus we got two different structures. Thank you. And thank you sir for the cooperation. And the same thing I can show you with this ball and stick model. I have made this model. Can anybody identify this molecule? It has a CH3 group and hydrogen attached to one of the double bonded carbon atom, and in another one also one CH3 group and another hydrogen attached to one of the other carbon atom. So what can be this molecule? Can somebody identify this molecule? Just say the name of. Can you say the name?
1,2-di-
CH3 group.
Zinc groups are at the opposite side of the double bond.
Yes sir.
And yellow group.
Yes, sir. Thank you, sir. But I just want to ask which molecule it is. That means here it has a CH3 group is there, and there is a CH double bond CH, and there is another CH3 group. So it has 4 carbon atom, and the double bond is on the second carbon atom. So which will be this molecule? It is butene. It's butene. And now we can see that in butene, the double bonded carbon atom has one CH3 group and one hydrogen on each of this double bonded carbon atom. And this is one possible arrangement in which the similar groups, CH3 groups, are on opposite side of the double bond. Now I can have another arrangement for the same compound that is butene with CH3 group on the same side of the double bond and 2 hydrogen atom on the same side of the double bond. So, and these two are geometrical isomers. So, and they actually they result by the restricted rotation of carbon-carbon rotation of carbon-carbon double bond, and the resulting different arrangements we are getting. Due to that, we are getting, and thus they exhibit geometrical isomerism. And these are the two types of geometrical isomers. And in one isomer, the similar group is on the same side of the double bond, and in the second isomer, the similar groups are on the opposite side of the double bond. So when similar groups are coming on the same side of the double bond, it represents the cis isomer. And when the similar groups are coming on the opposite side of the double bond, it represents the trans isomer. So these two are the geometrical isomers of butene, cis isomer and trans isomer. They are geometrical isomers. So let us see the definition of geometrical isomerism. So they are the stereoisomers having same molecular formula and same structure, but they differ in the arrangement of atoms or groups attached to the double bonded carbon atoms. And the phenomena is called a geometrical isomerism. Now, so we have already learned about cis isomer and trans isomer. So it is possible in complex of the type C, X, Y, double bond, C, X, Y. This is one possibility where two different groups are attached to the double bonded carbon atom. This is one case of alkene in which we can see geometrical isomerism. Now, we can also have other structures. For example, I am changing this CH3 group with one hydrogen here. I'm just fixing one hydrogen over here. So now it is CH3, CH, CH2. CH3, CH, CH, double bond, CH2. CH2, double bond, CH, CH3. So can you identify this molecule? Can you identify which molecule it is? It is propene. Thank you. And so here in propene you can see that here on one of the double bonded carbon atom, two hydrogen atoms are attached. On the other double bonded carbon atom, one hydrogen and one CH3 group is attached. Now, can we interchange the position and get geometrical isomers for this compound? Do you think? So let us see. Let us interchange and see. This side, anyway, two similar groups are attached to this carbon, double bonded carbon. So let us change this one. So I'm just exchanging their position. I'm just fixing CH3 over here. Am I getting a different compound? No, I'm getting the same compound, propene only. So that means in propene, can propene exhibit geometrical isomerism? No, it cannot. Why? Why it cannot exhibit? Because it has two similar atoms attached to the same double bonded carbon atom. That's why whichever way we try to exchange, we get the same structure. So what's the condition for exhibiting geometrical isomerism? Let's see. So the first and foremost condition which I told was the double bonded carbon atom should have two different atoms attached to the two different atoms or group attached to it. So in propene, since two similar atoms are attached, it cannot show geometrical isomerism. Now here are different possibilities. We'll check whether they will exhibit geometrical isomerism or not. In the first case, you can see in this molecule, two different groups are attached to the double bonded carbon atom. So can it show geometrical isomerism? Yes, it will show. Both sides different groups. And second compound you can see on the same side, similar groups are attached. That side also similar groups are attached. So can it show geometrical isomerism? No. So it's violate the condition for geometrical isomerism. And what about this one? The third compound, two similar atoms on one side and two different groups attached to other side. So what about this compound? No, because on one of the double bonded carbon atom, two similar groups are attached. So this also cannot show geometrical isomerism. What about the last compound? Again, it can show because it satisfies the condition. Now, we can also see geometrical isomerism in the case of molecules of the type CXY double bond CXZ, and also of the type CXY double bond CZW. So here this is CXY hydrogen and H3, and this is same one similar group here, so it is XZ. So it can, even if we change since two different groups are attached, it can show geometrical isomerism. And now if I am changing this with chlorine, here also two different groups are attached here, but this became a special case of geometrical isomerism, that is Z and E and Z notation, where if four different groups are attached to the double bonded carbon atom, we have to use the term Z and E instead of cis and trans. Z means we have to determine the priorities of the atoms and groups attached to the double bonded carbon atom according to the rules. Mostly the groups with a higher atomic mass, they will get higher priority. So if the prior groups are coming on the same side, it is classified as Z isomer, and if the most prior groups are coming on the opposite side of the double bond, it is classified as E isomer. So these are the different possibilities in geometrical isomerism in alkene. Now I have some questions with me regarding geometrical isomerism. Let us see. So here you're asked to write the geometrical isomers of this compounds. So the first compound is CH, Cl double bond, CH, Cl.
Give it as a homework.
So first we should show carbon-carbon double bond, and we should show the other two valencies attached to the double bonded carbon atoms. And this is first isomer, and the second isomer. This is first isomer and second isomer. By keeping the two atoms attached to one of the double bonded carbon atoms same, we can interchange, and we get cis and trans isomer. Like that, you can solve the other questions, and we can check whether they will show geometrical isomerism or not. The second compound, since two different, so they will show. You can draw the geometrical isomers as a homework you can do. And in third compound, will it show geometrical isomerism?
No.
No, because two similar groups are attached to it. And
One, no.
fourth
No.
compound, no. And
Third one, yes.
fifth and sixth, they will show. So you can make the cis and trans structures of these compounds as a homework. Thank you.